Hello, today we're going to be looking at section 5.5 and we're going to talk about multiple angle formulas. Now this section actually deals with four types of identities. Those involving multiple angles, those involving squares, half angles, and products. But today we're going to focus on just one type of identity, and that is the double angle formulas. Now there are three double angle formulas that we are going to focus on today. The first one is sine of 2u. Sine of 2u can be broken down into 2 sine of u cosine of u. The double angle formulas are probably the most commonly used formulas that we will see in this particular section. And what it allows us to do is take a larger angle and break it down into a smaller angle that is basically half of what we started with. Now, where does this particular formula come from? You might see a bit of a relationship to the sum formulas that we took a look at in the last section. And in fact, that's exactly where they come from. So if I'm trying to come up with this formula, we can take a look at a very quick proof of this. Sine of 2u can be rewritten as sine of u plus u. That's really what sine of 2u is. And notice we can now apply the sum formula for sine, which tells us that sine of u cosine of u plus cosine of u times sine of u. Instead of a u and a v, notice we now have u's in both spots here. And notice that I'm really adding the same two expressions together. So we can simplify this into 2 sine u cosine u. And so that's where this particular double angle formula comes from. Now the second one I want to take a look at has a few more parts to it. It is cosine of 2u. Cosine of 2u actually has three different formulas we can use. It's similar to the Pythagorean identities in that regard. So cosine of 2u, one of the forms we look at is that it's equal to cosine squared u minus sine squared u. And in fact, if we wanted to look at a proof of that, we can again apply the sum formula here. So we can take cosine of 2u and say that's equal to cosine of u plus u. Now when we do that, we apply the formula, which says that we have cosine of u times cosine of u minus sine of u times sine of u. And I think you can see very quickly where this first formula came from. It does equal cosine squared u minus sine squared u. So this is the first version of the formula that we can take a look at. But now if I take that and rewrite it, I can create two other versions of this particular formula. In fact, if I start by rewriting sine squared u using the Pythagorean identity, notice I would come up with cosine squared u minus, now remember sine squared u is 1 minus cosine squared u. Again, it's important to look at it in parentheses because we are subtracting both the 1 and the cosine squared u. And this becomes cosine squared u minus 1 plus cosine squared u. So another version of cosine 2u that we can come up with is 2 cosine squared u minus 1. So that's another way it can be written. And what's nice about this is that you only have it in terms of cosine. Up here we have cosine squared and sine squared. Now the third one would be again going back to this original one we had, but instead of replacing the sine squared u, let's replace the cosine squared u. So if we were to do that, again, cosine squared u would be 1 minus sine squared u minus the other sine squared u that's in the formula. And here we would end up with 1 minus, and notice we now have 2 sine squareds of u. So this would be the third version of the formula, and it would be in terms of just sine. Notice with the cosine squared, 2 cosine squared comes first and it's minus 1, and with this one it's 1 minus 2 sine squared u. So they are kind of reversed. So I like to remember this first one, and if I need to, I can very quickly generate these other two formulas. Now the third double angle formula that we want to take a look at involves tangent. Tangent of 2u is equal to, very similarly, the sum formula, 2 tangent u over 1 minus tangent of tangent squared of u. There we go. Should be a square there. And this one also can be very quickly proven using the sum formula for tangent. So remember with the tangent to u, if I look at it as tangent u plus u, I end up with tangent of u plus tangent of u over 1 minus tangent u times tangent u. So you can very quickly see how we come up with the formula. Again, it's 2 of the tangent u's over 1 minus, and now we're multiplying, so it's tangent squared of u. So let's take a look at how these can be used, or how you might be asked to use them. Now the first way that we might take a look at it is in an equation where we're asked to solve an equation. So for example, let's say that I want to find all the solutions of the following. Sine of 2x plus cosine of x is equal to 0. Now the first thing you'll notice is that these are not both in terms of the same angle. So I can't solve it the way it's written. So I need to be able to rewrite one of these in terms of the other one. The most logical one would be to rewrite the sine of 2x in terms of just an x. So sine 2 of x, if you might recall from the formulas we just looked at, I can rewrite as 2 sine of x cosine of x, using the identity we just looked at, the double angle formula. So now I have 2 sine x cosine x plus cosine of x is equal to 0. This should look familiar to other problems that you've solved now. Now, what strategy do I use here? Well, I have two terms that seem to have a common factor in them. So what I'm going to do here is pull out that cosine of x, and then what I'm left with is 2 sine of x plus 1 is equal to 0. So basically, I have my zero factor property, which allows me to say that cosine of x has to equal 0, or 2 sine of x plus 1 has to equal 0. And I can solve those two down. Now, when does cosine of x equal 0? Well, again, there's two spots where it equals 0. That's at x equals pi over 2, or at 3 pi over 2. And what about 2 sine of x plus 1? Well, I need to solve that for sine first of all. So if I move the 1 over, I get 2 sine of x is equal to negative 1. If I divide both sides by 2, I get sine of x is equal to negative 1/2. So when does sine of x equal negative 1/2? Well, you might need to think about your triangle if you don't have this one memorized yet. So let's see, 1/2. I bet that's in a 30, 60, 90 triangle. So I've got pi over 6, pi over 3. Let's see, where does that go? 1 root 3, 2. And so 1/2 is opposite my pi over 6. Now, in which quadrants am I going to be in? So now I want to think about my unit circle. Sine is going to be negative in the third and the fourth quadrants. So if I think about my reference angles of pi over 6 in those two quadrants, this first one is going to be x equals 7 pi over 6. And the second one here is going to be 11 pi over 6. Now those would be my solutions in the unit circle, 0 to 2 pi. But remember, my original problem, I asked you to find all the solutions. So that means I need to look at all the possible combinations. Now we've done this before, so we can take a look at what we have here and break it down. Now the smallest way to write pi over 2 and 3 pi over 2, because we're up here at pi over 2 and 3 pi over 2, they're pi units apart, we could write that as x is equal to pi over 2 plus every pi n, where n is an integer. With these two, again, there's different ways you can choose to write it, but I would go with the simplest version. In that 7 pi over 6, I'm going to need to keep going around each time to that. So that's going to equal 7 pi over 6 plus 2 pi n. And finally, I have my 11 pi over 6 plus 2 pi n. So that reviews again a little bit solving equations as well, because the only thing new to us on this problem was actually replacing sine 2 of x with a double angle formula so that we could actually solve this particular problem. So that's one way that we can look at solving it. I'm going to stop here for now, and in the next video I'll show you a couple more examples using these identities.